Okay, so now let's continue. Here below you will learn how to how we can use how we use 193 nanometer wavelength to obtain 5 nanometer resolution. So we will use immersion lithography of X-ray illumination, phase shift mask, optical proximity correction, and double processing. So among those techniques, so immersion lithography is one of the major trends for the lithography systems. Another one is the double processing is also a major trend for the lithography. So all the other three is relatively small trends. So actually, in the 1990s, so Nikon and Canon, those two Japanese companies, they dominated lithography tools. So even for today, if you go to the clean rooms, so many clean rooms for the universities and also for the MEMS, and also for the LED, for LED chip. So they do not need the state-of-art lithography system. So they all bought those places. They all bought the Nikon lithography system that was made in the 1990s and abandoned by the no longer used for the IC manufacturing. Then they are as a second-hand equipment. They are used for those applications. So Nikon really dominate the lithography tool in the 1990s. So after 193 nanometer, there are two routes to get higher resolution. So we know that the resolution given by K1 lambda over NA. So this is the resolution. So one way is to reduce the wavelength. So this is what Nikon has tried to do. So it spent lots of effort to go to 157 nanometer lithography. So this is for the case of this excimer laser. So this is excimer laser. Another route is to go to the bigger numerical aperture, so which is the immersion lithography. So this company, this Netherlands company, ASML, put more effort in the immersion lithography. So in the end, so in year 2003, the Intel abandoned 157 nanometer route. So as a result, so Nikon had to abandon 157 nanometer as well, and it shifted to 193 nanometer immersion lithography. But at that time, because ASML started immersion lithography earlier, so by 2004, it had already dominated lithography market. But Nikon also got the immersion lithography product in 2005, but it is already too late. So because of this, so one went to shorter wavelengths, 157 nanometer. So this one went to the immersion lithography. So in the end, the immersion lithography went out. So because of this, so today ASML is the dominant lithography tool manufacturer in the world. So the tools sold by this company is far more than that of the Nikon and the Canon combined. So this is one reason. Another reason, as we will see later on, is also because this company developed EUV lithography, but the EUV lithography, Nikon and Canon, they're out. They are not in the EUV lithography business. Okay, so now let's go to the immersion lithography. So the idea is simple. So we do the lithography in a liquid that has the index higher than 1. So actually, the immersion is not new for optical imaging. For the optical imaging, people have been using oil immersion for the optical imaging for more than a century. So so there is a sample, you put a drop of the oil, then you have the lens. When you put a drop of oil between the sample and the lens, you get higher resolution for the imaging. But for the lithography, for the immersion lithography, it is far more complicated. So you can imagine, so today, it takes about 1 second. It's only 1 second to expose one dye. So 1 second to expose one dye. If we do the immersion, so we have to do the water coming in, stage movement. So water coming in, exposure, water come out. Everything has to be done in 1 second. And also, we cannot tolerate any contamination. You can imagine if you do things in the water, there may be some particles in the water, there may be some air bubbles in the water, other things. As a result, So immersion lithography had at the beginning, it was thought that this is not something practical, but later on we know that this is actually, around year 2004 it became commercialized. Another similar, sorry. So another similar technique is the CMP, which is the chemical mechanical polishing. I think you have learned CMP in the previous course, NE353. So because of the development of the chemical mechanical polishing, so the interconnection shifted from aluminum to copper. But the CMP is also considered something really, is also considered something that will never work. So because this also looks like a dirty process. So you put lots of particles and you do the polishing, so it looks really dirty. But actually, it became the practical also about 20 years ago. So because of this, it shifted from aluminum to copper for the metal interconnection. So what is immersion lithography? So the idea is simple. You can imagine there are two ways to think about this. So first, you think about numerical aperture, which is given by n sine theta. So you can imagine when you have bigger refractive index higher than 1, you get higher numerical aperture. Another way you can think of it is that you can put the n up. So this way you have the smaller wavelengths. So when you have the light go through the liquid, you have the wavelengths become shorter. So when you have a shorter wavelengths, you get better resolution. So this makes sense. So if you put everything in a water, you put everything in a liquid, and you use the less material. The less material has also to be modified. So you use the less material that has index multiplied by the n water. So this way everything will be the same, but you get higher index, shorter wavelengths, so you get a better resolution. So for the case of water, so n equal to 1.44. So this is higher than this is for the 193 nanometer. So effectively, so 193 divided by 1.44, you get 134 nanometer. So effectively, we use 134 nanometer wavelength for the lithography. So we know that for the water, n equal to 1.33. So this is the index for the visible light, for the visible wavelength. So this is the index for at 193 nanometer. But in reality, we do not have to put everything in water. So it is not practical, also not necessary. So all we need to do is we put a liquid. So we put the liquid between the objective lens, and the wafer. So all the other places is the same. It's dry. So only this place we put some liquid. So for the requirement of the liquid, so first it has to be low absorption, has to be transparent to 193 nanometer. Secondly, it has to be compatible to the photoresist, so it cannot attack the photoresist and the laser material. Thirdly, has to be uniform and clean, very pure, not contaminating the lithography. So the water turned out to be a very good material. So the index 1.44, not so high, but it is okay. Absorption is also low, and also it can be very pure and no contaminating. But nevertheless, in the past 20 years, so the industry also looks hard to other materials that have index, that have n bigger than 1.44. Also spend a lot of effort to study other materials. But in the end, so all the other materials, that even though they have higher index, they have other problems. So in the end, so even for today, so we still use water for the lithography. So we have seen the reason for the higher resolution when we're using water. So fundamentally, the light is a carrier of the information on the mask. So more light is collected to form the image, the better the resolution. So one way to do this, as we have seen, we make the lens bigger. So we have bigger lens, you collect more light. You collect more light, so you get better image. Another way you can, as you see here, when you have the water, when we have the liquid, we also collect more light. So here we look at the details. So the index for the water is 1.44, that for quartz is 1.56, and for the resist 1.75. So you can see here, for the casing of the iron, so the maximum light we can collect is 0.9. So in theory, you can go to 1.0. You can go to the 90 degree. So even the light come out. So even though the light come out this way, you can also collect it. But in reality, we have to make the light something like this. So the angle here, the sine this angle is 0.9, not 1.0. So for this angle, I will do it in the inside of the lens. This gives you, so sine theta inside of the lens corresponds to 0.9 divided by 1.56. 1.56 is the index for the glass. So this is because of the about the Snell's law. So N1 sine theta 1 equal to N2 sine theta 2. Right? So this is the N1 sine theta 1 equal to N2 sine theta 2. So because of this, we can calculate the angle inside the lens, which is given by sine theta equals 0.58, theta equals 35.5 degrees. So the light inside the lens within this angle, it can be collected. More than this angle, it cannot be collected. For the total internal reflection, so this corresponds to the case that the light cannot come out. So this is given by N1 N sine theta, so N sine theta equal to 1, so offset is 1, times sine 90 degree, so equal to 1. So this give you about 40 degree. 40 degree, we have total internal reflection, and for the case of 0.9 degree here, 0.9 sine theta, we collect light up to 35.5 degree. So when we have the water, we do some similar calculation. So sine theta inside, so inside this angle here, sine theta here is given by 1.44 times 0.9, which is this angle here, divided by the index of 1.56, given by 56 degree. So the light up to 56 degree can be collected. So obviously, when we put the water, we collect more light. So that's why we get a better resolution. So this is some fundamental physics. But if you do not want to go to the physics, you can just consider this formula, you get the same conclusion. So we have a look at how to improve the numerical aperture. Now we look at the K1 value. So this is something complicated. So anything not related to lambda and NA is put into this K1 factor. It depends on many things. For example, it depends on the property of the photoresist, the contrast of the photoresist, the use of the resolution enhancement technique that includes the resolution enhancement technique that includes off-axis illumination, phase shift mask, optical proximity correction. So those things they can all improve the resolution. Then we say that those things help to reduce the K1 value. So here is also those three things is also put in here. For the illumination optics, so we can work with the off-axis illumination. For the photo mask, we can do two tricks. One is the phase shift mask. The other one is optical proximity correction. For the photoresist, we can do top surface imaging. So that means we use a thin layer over the resist. Then we put another layer below it. So we do the lithography on the thin resist. Then we transfer the pattern to another polymer layer or carbon layer. Then we transfer the pattern to the substrate or to other part. This is the top surface imaging. We use very thin resist layer on the very top. We can also use the anti-reflection coating. So when we have the resist, actually this is not optional, so we have to use it. There must be a layer with anti-reflection coating, because otherwise, so when the light comes in, if that reflects back from here, then there will be the incident light and the reflected light, they will interfere. You form some patterns on the profile, so this is not good. So the anti-reflection coating is always utilized for the lithography. So then there is double exposure and double patterning. So here below we will talk about off-axis illumination, phase shift mask, optical proximity correction, and double exposure and double patterning. So the first one is off-axis illumination. So you can see that we have seen this slide. So when the light passes through a grating mask, so there is diffraction. So this is the lens, and this is the image. So normally we do the along axis illumination. So in this case, this part of the light gets collected to form the image. So this part, the purple color light gets lost, diffracted, lost. If we do the off-axis illumination, so this part is collected, so this part is lost. So here is the schematic. So you can see, so the drawing is only schematic, is not to scale. So actually, the size of the photon mask is much smaller than the size of the lens. And also the light, obviously, they do not come from one slit. They come from all the slit, not from this one slit. So in this case, you can see that the 0 order and the -1 order, +1 order, you can see the order here, first order, second order, minus first order, minus second order. So the 0 order minus +1 order light got collected. If we do the off-axis illumination, so this become the 0 order. So the 0 order means this light, this one is parallel to the incident light. So this is 0 order, this is first order, this is the second order. But you can call it -1 or -2 to the left side. It's the same thing. So now the second order of the light can be collected. So as we have known before, if you look at this one, this one. So this is m equal to 1 corresponds to the case of first order, m equal to 3 corresponds to the case of the second order. So when we have m up to 3, you can see the image becomes something like this. So it is closer to the square pattern. And that means the corners, the details of the mask pattern can be better resolved than the case if we have only m equal to 1. For if we collect light only m equal to 1, we have this curve. This curve, you can see, is farther away from the squares. So the corners of the detail is not resolved. So how to do this? So this is the aperture we can use. So this is the correspond to the normal exposure. So this one is off-axis illumination. So this one is called annular. So this one is called a quadruple. So you can imagine for the case of the quadruple, it is most effective for vertical or horizontal line and space patterns. So line and space pattern is the same as the line array or grating. So we call it a grating. It's good for the vertical or horizontal grating patterns. But this one is symmetric. This one is less resolution enhancement, but it is orientation independent. So you may ask, so how to realize off-axis illumination? It looks like complicated, but actually this is the easiest and cheapest resolution enhancement technique. The state-of-art off-axis illumination apparatus, they are programmable, and it can be used for each different mask. So now let's look at how to do the light exposure from angle, no light from the vertical direction. So maybe I draw it here. So one way you can do this, for example, we have one light here, you have another light here, So those light, so that means this focal point is the focal point for this lens, and also so this focal point is the focal point for this lens and also the focal point for this lens. So if we have the light coming in like this, it come out the same way. If light coming in from here, if the light coming in from with angle here, and then this one the part here and also become an angle. So how to filter out the light coming through it? So what we can do, we put something here. For instance, if we block this spot, we have something like this. That means, so this is the focal plane. This is the focal plane. So this is the focal plane. So this part of the light goes through. So this part of the light goes through. So this part, the light gets blocked. So that means effectively we put this kind of shape. As the focal plane. Then this part of the light corresponds to the casing of this direction, right? So this direction of the light will go through. And the same thing, this direction of the light can also go through, corresponds to this spot. They also come to become this direction. So this way we have the kind of a cone. The cone shape of the light will go through for the exposure. So that means we just need to put those kind of apertures. We put this kind of apertures as the focal point and the focal plane of the first lens. Then we have another lens. Then the light will be what we want. So here we said we need to collect the light up to second order. So actually, we don't need. So this one I get it. So this figure I get it from the textbook. So later on I talked to the lithography people in the conference. So they told me we do not need second order. So all we need is first order. So in this case you can see for this normal illumination only zero order get passed through. So we have the light profile something like this. Only zero order, no pattern, just a blanket exposure. For this case, so we have minus one order. So zero order, so this one is zero order, minus one order, something like this. So we add them together, you get something like this. So you can see, so now we can see the periodic line array structure. Even though they are not so good, they are not like square, they are not so good, not square, but still we can see we have periodic line array. So the contrast is something like this. This is the light profile. Because we have only one minus one. So when we have both minus one and plus one order, if we have zero order, so if we have zero order, minus one order, plus one order, the light profile will be something like this. That means it goes to this point, go to the zero. But when we have only minus one, we get half, something like this. But still, this is good enough to resolve the line array pattern. So now we look at the second trick. Which is the phase shift mask. This is what we do on the photo mask. So this is the normal photo mask. So after the light goes through the photo mask, right after the photo mask, we have this amplitude profile, so square wave. Because of the diffraction, this is the amplitude on the wafer. Then, if we want to know about the intensity, which is the square of the amplitude, we get this light profile. So you can see it's not very good, because for this part, we wanted it to be no light. But because of the constructive interference, we got light at this gap. So to solve this problem, if we do something, so we make the 180 degree phase shift. Then the light, this one is the same, so this one become the negative opposite sign, because this pi shift half lambda phase shift. And then after diffraction, it become like this. If we add them together to get the intensity, you get this profile. So obviously, this profile gives you higher resolution than this profile. Now, this is the idea of the phase shift mask. So we shift the phase by 180 degrees. That corresponds to the half lambda extra optical path. So now let's look at what is amplitude and what is the intensity. So we know that for the light power, which is a vector, the light power we have direction equal to E cross H. This is also vector. So this is the light power. There is something factor in the front. There is some epsilon 0, mu 0 in the front. So the power is proportional to E cross H. So E is the electrical field component of the light, which is electromagnetic wave. So H is the magnetic field component of the light. So you can consider the amplitude. Amplitude is the E value. So this one, the E is the amplitude. H, the magnetic field component, is proportional to electrical field it is proportional to the electrical field component. So as a result, the power is proportional to E squared. So that's why we have the intensity equal to E squared, amplitude squared. So here I use the power. Later on we use the term I. I is also the intensity equal to E squared. So now let's look at how to induce this 180-degree phase shift. So this can be done by etching into the glass, as you can see here. So here this is the light from the air, then into the glass, then come out. So this one from air, then into the glass, then come out. In this side it is in phase. The two lights is in phase. After passing the glass, it is 180 degrees out of the phase. So this is because of the etched. This part is etched. So how deep we should etch? So this is related to the optical path. Optical path equal to N times optical length. So you can see for the case of this side, for this side, the optical path equal to N times the depth, edge depth. For this side, the N equal to 1, so equal to 1 times depth. So difference should be equal to lambda. So this number should be lambda divided by 2. Lambda divided by 2. So from here you can see that the thickness, the depth edge equal to lambda over 2, 1.56 minus 1 equal to 172 nanometer. So here the schematic. So this part you etched, the glass is etched. This part is not etched. So this way you get 180-degree phase shift mask. So here we need 2 patterning steps. So we need first pattern this part, then pattern this part, and with accurate alignment. As a result, the fabrication cost for the phase shift mask is 10 times that of the normal regular mask. So here we talk about this kind of configuration. So we have the 180 degree, 0 degree, 180 degree, 0 degree. For the other patterns, for example, if we want to expose this square, so this is the binary mask. So what do we do? There are a few ways to do this. You can you put some small structures here. So this part is transparent, but they are 180 degree phase shift. So we can also do it like this way, or we do the chromeless mask. This is chromeless mask. This one is attenuated mask. They can all be used to have better image contrast than this binary mask. So how come this one can give you better image contrast? For example, if you draw a line cross section here, so the light comes from the center part. You can see something like this. The light profile from the center part. The light comes from this part. Its opposite side is something like this. Opposite side, but it is smaller. If we add them together, so this part will cancel out this part. As a result, the transition will be sharper transition. You have sharper transition here. So we have the sharper transition here. You get a better image. So the same idea is here. and also here. So this one you can draw like this. So again, you draw this cross section. So you have the light. For the top part, you have something like this. For the top part, for this part, so this part is 180-degree phase shift, but we have some small transparency, 5 to 15% transparent. If I draw this part, it becomes something like this, maybe something like this. You can see that this part of the light can cancel out this part. As a result, the light transition will be sharper transition. It will be sharper transition. So we have the sharper transition. You get a better image. There is some light here, but because it is only 5 to 15% transparent, so the light here will not expose the resist too much. So this is the chromeless. So this one has no chrome. So every part is transparent. But this part, because we have 0 degree, 180 degree, they all cancel out. So those areas, they all cancel out. As a result, there is no light passing through, but there is light passing through here. So here's the comparison. For this case, this one is called alternating phase shift mask. Alternating phase shift mask. You have the 0 degree, 180 degree, 0 degree, 180 degree. So this is alternating phase shift mask. So this one gives you the best contrast. But the problem first, it is only good only for the periodic structures, which is the case for the memory cells like DRAM, SRAM, but not good for the random patterns like CMOS logic circuit. Another problem may be the phase conflict. For example, if we look at here, so offset is 0 degree, so inside is 180 degree. Then this part, there will be no light. The light here will cancel out. So in the end, after development, you get some extra structure in the resist. This is the problem. This is the limit for the alternating phase shift mask. For the attenuated phase shift mask, which is correspond to this case, for this one you can see the contrast is this curve. The contrast is this one, which is higher than this one. This one is the conventional phase shift mask. Sorry, there is no phase shift. This is the conventional binary mask, which is not, you can see, not as good as the attenuated phase shift mask. So now let's look at this one in more detail. This is called a chromeless. There is no chrome. So there is no chrome metal, transparent everywhere. So even for this one, you can see this is the binary mask. So we have block it, binary mask. This is the chromeless phase shift. This part is transparent, but it is very narrow. So in the end, so this part, 180 degree and 0 degree, they cancel out. So you have this dashed line contrast. So you can see this dashed line give you better contrast than this binary mask, this solid line. So how to make arbitrary patterns? If the pattern size is big, for example, this is a big pattern. This may be a big pattern. For the big area, you just put many small 180 degree, 0 degree together. So each of the square, each of the rectangulars, they are small enough so that they cannot be resolved by the lithography system. So in the end, the light see the average out. When you have average out, the light will cancel out. So you have the no exposure here. For the narrow, very narrow lines, you just put a thin stripe. Then you can see the same thing. You have the light cancel out. You get the line here. So now I want to ask you one question. If we have something like this, so this is a circle. So this circle, the radius is big. Say we have 10 micrometer, for example. So the radius is big. So we have this big circle. Inside the circle we have 180 degree. So inside the circle we have 180 degree. So offset we have 0 degree. So what will be the pattern after development if we have the positive resist? So think about this. So the only difference is that, so in this case, this line is very narrow, maybe say 10 nanometer, very narrow, much smaller than the resolution. But for this case, the radius is 10 micrometer. It's much bigger than the resolution. So the end result will be something like this. So those area, there will be resist left. So inside, no resist inside, no resist inside, no resist outside. But this area is also transparent. So even though it is 180 degrees, it is also transparent. So outside is transparent. So no resist here, no resist here. So only near the edge, only at the edges, at the edge. Sorry, not the edge. Only at the boundary between those two faces, we have the pattern left over. So now let's look at next one, optical proximity correction. Optical proximity correction. So we know that because of the diffraction, the sharp features are lost. So everything, the corners become, all the sharp corners become rounded. So we lost the information of the photo mask. But the good thing is that how much light is lost, it can be calculated. If it can be calculated, then we can do something on the photo mask to compensate the lost light. So this is called optical proximity correction. For example, so when we have this L-shape opening here, so the light profile will be the resist structure in the end will be something like this. So you can see this part become rounded, this part become lost. This will become lost. So this is the case for, you can see this is the negative resist. So exposed area remain. But this, you see, we lost some features here, and we also lost some features here, and we get something extra here. So to compensate this problem, so what we can do, we add some sub-resolution square, we added here. So the light come from here, will compensate the loss of the light here. So this part, we have too much light, too much exposure, so we take off a square. So this part, we have too little exposure, so we add something to exposure. So the key is that those things have to be very, very small. It is called sub-resolution. So the lithography system cannot resolve them. As a result, they will not show up in the final developed resist structure. So this is an example for the L shape. For the case of this more complicated shape, you can do the same thing. So this is a regular negative resist, regular without optical proximity correction. With optical proximity correction, you get this pattern. But here you can see there is a small mistake. You try to find out where there is the mistake. Where there is the mistake. So the mistake is here. Here is the mistake. So this part, if we have too much exposure, we have too much exposure. So this one should be recessed. This part should be taken away. Rather than add something. So this is the basis of the rule. So we know about this. So we add the structure. But when the feature size become even smaller and the pattern become more complicated, so we can do even better than this by numerical simulation. So this is called inverse lithography. Another term for this for the industry is called fabless. Non-fabrication, right? We do fabless. It's called fabless lithography. So there are many people to do this kind of lithography using the computer rather than using lithography equipment. This is called inverse lithography. So the idea is that we know what we want. We know we want this resist pattern. So we want this resist pattern. Then we work backward. So we work backward to find out the photo mask, to find out the mask design that can give you this kind of resist pattern. So every pixel of the mask has to be optimized by numerical simulation. So until we get the light intensity profile as we want. So as you can see here, we want this light intensity. So in the end, we need to get this kind of complicated mask design. For instance, you see something here, this kind of thing. It looks like very weird, but this is done by the numerical simulation, and this one will give you the light profile like this. This is called inverse lithography. We make the mask design by simulation to optimize every pixel of the photo mask. This is the summary for the optical proximity correction. So without without OPC, this is called conventional mask. So we have the feature size rounded. So this is the rule-based. So this one is the rule-based. So we know what to do by the experience. So this we add something, reduce something, we get better feature size for the smaller 130 nanometer. This is what I call the model-based. So we do the numerical simulation to design the photo mask. We get even smaller feature size. So this is what I said 100 nanometer. But actually today we get down to 7 nanometer by using this optical proximity correction together with other tricks we have seen so far. Okay, thank you.